this fundamental problem. I showed you right at the beginning that the pairing, anticodon pairing requires a very specific geometric arrangement of the two components. So now there's a fundamental problem. If the tRNA arrives on an angle together with EFTO, it will not be able to get into this correct spherical configuration unless something happens. And we found out what happens is that the tRNA, in the process of entering, changes its conformation. It gets this crooked conformation. That comes out from here, from three-dimensional images that show the ribosome in these different conformational states. Here's a state where a new tRNA is expected. Here the tRNA arrives along with EFTU, and it's in this crooked conformation, and here the tRNA is completely invented. So here you see the difference between the normal conformation and the crooked conformation of the tRNA. Here is the juxtaposition. Now, I'm just going to show you molecular dynamics simulations. It is possible for a mechanical system to make exact predictions. If one knows the initial velocity and initial position, then one can predict the trajectory of an object. And in the same way, if we have an exact description of a molecular structure and assign initial velocities to each atom, then we can make a simulation of how this molecule is going to behave in the future. And so somebody at Los Alamos, his name is Kevin Sanbomatsu, has undertaken this tremendous job of predicting the way the ribosome behaves. Now, the ribosome is a structure with more than 1 million atoms, and so he simulated the trajectory of all these atoms from a certain process. He was able to do the simulation because he had all these huge government computer at his disposal. So he made this molecular dynamic simulation starting from a structure that was inferred from our cryo-electron microscopy work. In other words, it was done from taking the ribosome and positioning the tRNA in this initial conformation as it approached the decoding center. But first of all, I'll just show you molecular dynamics simulation of a tRNA under thermal bombardment. All molecules undergo these kinds of stochastic fluctuations. And here's the simulation by Kevin Sanbomatsu. And that gives you an idea on how the tRNA, given the initial positions that we observe, so you're going to see is the tRNA always starting in the so-called AT position before entering the ribosome and then going all the way in. We're going to see this again from a different angle and close up. Okay, so from this it has become clear that in the process of entering the ribosome after the anti-codon recognition is taking place and the ERTU innovation factory goes all of the way, then the tRNA goes in like a molecular, in the process of a relaxation of a molecular spring, and sort of drags the amino acid group into the ribosome. But it's very interesting to see in this movie, there's a corridor that acts like a sieve that makes absolutely sure that not some kind of an unreasonable molecule is going to be incorporated there. So it's sort of a final quality insurance. So, all right. Now I'll talk about translocation a bit. So translocation, mRNA and the tRNA must move by the length of one codon. When EFG binds, the small subunit rotates with respect to the large subunit. And this has been discovered by Crio-Electron microscopy. We see this kind of rotation taking place. So when elongation factor G binds, then the small subunit rotates with respect to the large subunit. So essentially, you see the ribosome here in action. Each translocation requires this kind of ratchet motion. So it indicates a reorganization of the entire ribosome structure that facilitates the movement of the tRNA into the next position. And one can make atomic representation of the two different states by flexible fitting of X-ray structures. And then one can depict these kinds of internal molecular reorganization on the atomic scale. And other people have used fluorescence energy measurements in order to find out that there are actually distance changes between proteins that exactly confirm the existence of this ratchet motion. So just to mention what the ratchet motion is doing, if you imagine that the mRNA is closely locked with the small subunit, then the ratchet motion that we observe exactly performs what we expect. It moves the mRNA and tRNAs exactly in the right direction. What needs to happen next is that the lock opens. We already know what closes the lock. The mechanism that I mentioned was discovered by crystallography, the locking in by the two bases. And if we postulate that the lock opens in this position, then the small subunit can simply move back and the mRNA stays in place.